Hello, welcome to Stars, Cells, and God today. I'm Jeff Zweerink, your host, and I'm joined in studio by Dr. Hugh Ross. We're going to be talking about little red dots and Big Bang cosmology and whether the universe is a simulation or not. Hope you enjoy our conversation.
The paper is right here, published in Astronomy and Astrophysics, and 28 authors,
Okay.
mainly Americans and European astronomers, using the James Webb Space Telescope. It's a 20-page paper, a lot of dense stuff in here, but I'm going to try to break it down.
So remind us again, why are these important from an apologetic perspective?
Well, they're important because a lot of people, atheists and young Earth creationists, have been pointing to little red dots, saying the Big Bang is wrong, and atheists are saying, hey, there really isn't a creation event like the Bible describes, and then young Earth creationists say, hey, the universe really isn't billions of years old, and so what's going on with these little red dots? And it'd probably be good to define what we mean by little red dots.
No, that would be good. Okay, so this is an issue of whether our current understanding of science and cosmology is correct, and does it point to there being a creator? This is basically the question we're addressing here. So what are these little red dots?
Okay, they're basically the emerging cores of galaxies. And so what I've noticed is young Earth creationists, including those with PhDs in astronomy, have been making the claim that the James Webb Space Telescope is seeing fully developed galaxies in the very early universe, which is incorrect. They're not.
All right.
The earliest fully formed spiral galaxy we see has a redshift of 5.2, which corresponds to the universe being 1.15 billion years old. And actually, our own Milky Way galaxy was fully formed when the universe was 1 billion years old. These little red dots are talking about galaxies that are 200, 300, 400, 500 million years after the Big Bang creation event. And, they're not big galaxies like we see in the universe today. They're the cores of what will become big galaxies.
Okay, so just kind of take a step back here, if I could. So the James Webb is seeing into a new region of, not quite a new region of space.
Well, they call it the cosmic dawn.
No, that's fair. It's seeing a region that we've not been able to observe before,
right?
Largely because we can just see things further away, which means older in time.
Yeah.
And it seems like there's little red dots. I'm presuming that comes from the fact that these look like little red dots in the James Webb Space Telescope images.
Yeah.
Okay.
Yeah, they're tiny.
And so how does that contrast? Because I know the James Webb has been seeing galaxies that have far more stars. They're far bigger, far more complex. This is not what you're talking about here, correct?
James Webb is finding those galaxies.
Okay.
But we're seeing those galaxies at redshifts 5 or less. And the Hubble Space Telescope is seeing galaxies like that as well. James Webb is seeing them in more detail and saying, hey, these galaxies have fully developed spiral arms. These little red dots, we're not seeing fully developed spiral arms.
Okay, so
what we're seeing are the cores of what will become fully developed galaxies.
Okay, so there's two separate phenomena that we're addressing there, and it's important just to not confuse. Okay, so go ahead and tell us what we found with the little red dots.
That the little red dots are what you're going to see in the very early universe, because the cores of galaxies are the brightest part of the galaxy. That's true of galaxies today. The cores are much brighter than the outer spiral arms. So that's what James Webb is going to be able to see.
So is it the James Webb is just seeing cores, or the James Webb is just seeing cores of galaxies that are bigger?
They're seeing just cores because the James Webb is powerful enough that if there were fully developed spiral arms, it would be able to see them.
Okay.
They're not seeing them. They're just seeing these cores. They're also seeing that the cores are small, much smaller than the cores of galaxies today, and they're also red, indicating we're seeing stars that are youthful. They're stars that are just forming. So a lot of new forming stars, very compressed, compact together.
Okay.
And the controversy over these little red dots is, how can you have these cores of emerging galaxies that bright if all the light's coming from stars?
Okay.
And that was a challenge we talked about back in January when they were first discovering these little red dots. They seemed to be too bright. And so this paper basically explains why they're as bright as they are.
Okay. So if I remember the discussion there, if this is all from stars, you've got to have a whole lot of star formation happen in a few 100 million years, 250, 300 some million years. And to get that much star formation to happen that quickly, that's just a problem.
Well, there's another problem
What's
too.
the other problem?
And that's getting the little red dot as small as it is. If
Okay.
it's all stars, you'd expect the core to be bigger than what we observe.
Okay.
So there's several problems if all the light indeed is coming from stars. Now, what the James Webb has recently been able to do, these 28 astronomers, they got a very detailed spectrum of the brightest of these little red dots.
Okay.
So they perfect focus. Let's go after the brightest one where we can get a really good spectrum. And so it took a lot of integration time, but they were able to get it and got a good spectrum. And what the spectrum revealed is almost no metal lines. Now, just to help people who are not astrophysicists, we astronomers call an element a metal if it's anything heavier than hydrogen and helium.
I know that was the funniest thing to learn when I was in graduate school. It's like, that it's like there's hydrogen, there's helium, and there's everything else.
Everything else is called a metal. Well, it kind of makes sense because the hydrogen and helium adds up to 99 to 98%.
Right. Oh, no, it does.
The rest of it is just 1 or 2%.
Right.
But their point was, if the light is coming from stars, almost all the light's coming from stars, we would be seeing metal lines. We'd be seeing carbon, oxygen, nitrogen.
Why is that? Because presumably these are some of the first stars that have ever formed. Wouldn't you just expect them to be mostly hydrogen and helium?
You would if all the stars are small.
Okay.
But if you've got a bunch of massive stars in the system, as you know, the greater the mass of the star, the faster it burns up, and it burns up with a fourth power of the mass of the star. So if you got a star that's 10 times more massive than the sun, it's going to burn up 16 times faster than the sun will. And at the end of nuclear burning, you're going to get the production of a lot of carbon, oxygen, and nitrogen. Those are the first elements you see that are heavier than helium.
Right.
And then eventually you get magnesium and iron and a whole bunch of other elements. But the first ones you'll see will be carbon, oxygen, nitrogen.
So what? Just for recollection here, how quickly does a star? I assume we're talking stars to be this bright and to account for this need to be, 10, maybe 100, maybe even 1,000 times as bright as the sun or more massive. Correct?
Well, if they're 100 times more massive than our star, the sun, and we know that at least some of them must be.
Right.
That's even true of stars today. You can get a few that are 100 times the mass of the star of the sun. They start making carbon, oxygen, nitrogen in less than 1 million years.
Okay, so the fact that we're seeing these a few 100 million years after the Big Bang, stars form, it'd be, for this to be these first stars and to not, and it would be fortuitous, could we be catching them just right after they formed, and yet we see them at multiple different epochs, or, 250, 300, 400,000. So it would just be really weird for it to be the first set of stars that are growing there. Is that what you're saying?
Yeah, and I'm saying if it's stars, you'd have to be seeing strong carbon lines especially.
All right, okay.
They're not seeing that, which tells them most of the light that they're seeing from the brightest of the little red dots cannot be coming from stars. It has to be coming from another source. And what that source would be a supermassive black hole in the center of this little red dot. And, if you've got a supermassive black hole, gravitationally accreting a lot of gas and dust from these new forming stars, then you're going to get really bright light being emitted just outside the event horizon. I mean, these are the brightest things we see in the universe. It's what we call a quasar.
Okay.
It's the brightest thing we see in the universe because a quasar is essentially a really big supermassive black hole that's sucking in huge quantities of gas. And as that gas approaches the event horizon of the black hole, the matter in the gas gets converted into energy with between 10 and 42% efficiency.
So, I mean, quasars, quasi-stellar radio sources, we detected those in radio waves, but we're seeing this here
in
optical or infrared, which
optical's
been shifted there. So why the difference there? I mean, if quasar, you'd expect it to be radio emission, correct?
Quasars emit at all wavelengths.
Okay.
I mean, X-ray, infrared, optical, they're probably easiest to detect at radio wavelengths. I mean, that's what I did for my PhD.
Right.
I was using radio telescopes to discover quasars, then other astronomers would follow up and say, hey, if we're seeing it at radio wavelengths, maybe we can get it at optical wavelengths, and then figure out the distance, etc. So in one sense, these little red dots are emerging quasars, which means most of the light is not coming from stars. It's coming from a black hole in the core of this little red dot that's accreting huge amounts of gas, where the gas is being converted very efficiently into energy. And to give you a comparison, when a star fuses hydrogen into helium, it's converting matter into energy with 0.07% efficiency. A supermassive black hole, 10 to 42% efficiency.
Right.
So it explains why even if you only have a supermassive black hole, let's say 500 million times the mass of our star, the sun, at that point in the history of the universe, it's going to be really bright. It's going to be easy to detect. And so
is this something you can detect? I mean, I know enough about quasars to know that they're not the same brightness at all wavelengths. Part of the reason why you detect them in the radio is that they're brighter there. Could you detect these things in radio waves?
Well, we don't have a telescope yet that's got the resolving power and the collecting power to pull that off.
Okay, so we do with the James Webb and the infrared, but not something in the radio wave.
Radio astronomers are eager to get an instrument capable of doing that, but infrared and optical right now is the way to go.
Gotcha.
And that's one of the reasons why the James Webb was put up there. Let's see if we can find what's going on in the very early universe. And quasars at infrared wavelengths are quite bright, so it's not that much of a limitation. And they purposely picked the brightest of these little red dots to get this detailed spectrum. As I looked at the end of the paper saying, hey, we need to go after the other little red dots.
Right.
Get more observing time. As you're aware.
Out of curiosity, how long did it take to get the data for this one, the brightest of them?
I forget.
All right.
It's been a while since I read this paper.
No, that's fair. I was just curious whether it was like an hour or whether it was a few days, because I know you're using a telescope where observing time is a premium. So.
Yeah, it's more than a few minutes.
This
is a very long, probably a day or two. I do remember reading that in the paper, but hey.
I mean, my recollection was even just the kind of the equivalent of the Hubble Ultra Deep Field measurements, which the Hubble took 11 days to do, was on the order of 12 hours to get that. So I imagine it's got to be at least 12 hours because you're seeing these little red dots and then even going deeper. So
yeah, it's one thing to detect the little red dot.
Exactly.
To get a spectrum of the detail they got requires an order of magnitude more observing time.
Yeah. So this could be the equivalent observing program of the Hubble Ultra Deep Field. That level of numbers
Probably
of days.
Not that level, but it'd be days as opposed to. I think
I agree.
Hubble Ultra Deep Field, that was like 2 weeks.
So, it was 11 days. That's I just happen to remember. There's some interesting numbers that play out in there. So,
but the bottom line is just saying, hey, now that we've done it with one little red dot, let's go after the other ones. And this also gives us some information. Okay, if we're not seeing strong carbon, oxygen, and nitrogen lines, that will give us a clue to how much of the light is coming from this supermassive black hole in its core, which means we can get a good estimate of the mass of that supermassive black hole. And already the James Webb Space Telescope has detected 3 early emerging galaxies, cores of what will become future galaxies, where they determined that the supermassive black hole was coming in at greater than 500 million times the mass of our star, the sun, and one even greater than 1 billion times the mass of our star, the sun.
So give some context for that, because I know getting massive black holes as massive as what we see in the centers of galaxies, that is, I wouldn't say it's a controversy, but it is like, how does this happen? Because we see black holes, I know at least some that are up to 1 trillion times the mass of the sun. Is this helping resolve some of that? Or those numbers are numbers, so throw out why that's a big deal, or explain why that's a big deal.
Well, here's our Milky Way galaxy. It's 13 billion years old.
Okay.
It's got a supermassive black hole that weighs 4 million times the mass of our star, the sun.
Okay.
And all galaxies as big as our Milky Way galaxy have supermassive black holes. Ours tends to be on the small side. The Andromeda galaxy has an average-sized supermassive black hole. It's 140 million times the mass of our star, the sun.
So that's like 100 times larger than the one in the center of the Milky Way.
35 times bigger.
You said 4 million. Okay, 4 million to 140. Okay, so.
Yeah. But if you go into the center of the Virgo cluster of galaxies, you've got M87 with a supermassive black hole of 6.5 billion times the mass of our star, the sun, which is one of the biggest ones discovered. Mm-hmm. What's interesting to astronomers is we're finding within the first 500 million years after the Big Bang creation event, these little red dots, where a few of them have supermassive black holes that are approaching or a little more than 1 billion times the mass of our star, the sun. This raises a question. It's one thing to understand how M87 has a huge supermassive black hole, because it's, 14 billion years old, or 13 billion years old, but this is stuff that's only a few 100 million years old. How can the black hole grow that fast? Mm-hmm. And that's what was interesting about the paper, and something we talked about when we did our workshop on what the James Webb Space Telescope was discovering. To get supermassive black holes that early in the universe, some of the firstborn stars have to exceed 500 times the mass of our star, the sun, and likely 1,000 times the mass of our star, the sun. Because typically how these supermassive black holes form, you get these really massive stars. They burn up very quickly, literally in hundreds of thousands of years. And if they're in a binary system, they'll quickly merge together and become a big black hole. And then you get several of those systems merging together. You can get a supermassive black hole. And that's kind of the bottom line here. This little red dot must have a really massive supermassive black hole, which means the firstborn stars, a lot of them have to be 500 to 2,000, maybe even 10,000 times the mass of our star, the sun. And even before the James Webb Space Telescope went up, we knew that once you've got carbon, oxygen, and nitrogen dust in the universe, that stops stars from forming that are bigger than 140 to 150 times the mass of our star, the sun. And indeed, those are the biggest stars we see. But if you're talking about a Big Bang creation model, that model predicts that the universe begins with only hydrogen in the periodic table, and after 4 minutes, you got 75% hydrogen, 25% helium, and nothing else. And so if you got nothing else, then the limit on how big the star can be is lifted. You can get stars coming in at many hundreds of times the mass of our star, the sun, if they're forming where there's no carbon, nitrogen, or oxygen to interfere with the star formation. And that's kind of been the quest of the James Webb. Hey, it'd be really cool if we can find out what is the distribution of star formation masses in the universe where there's nothing but hydrogen and helium. And astronomers have already discovered a halo cloud orbiting one of these little red dots where a spectrum showed that it only had hydrogen and helium. So that's a major prediction of the Big Bang creation model.
Right.
This is a follow-up saying, hey, this tells us that indeed we're getting really massive stars forming. For that to be the case, the Big Bang creation model must be correct because it predicted that the universe begins in its early history with only hydrogen and helium.
So now, a couple kind of apologetic questions I have in there. It seems like, so we see galaxies today, spirals, elliptical, spherical galaxies, big galaxies, small galaxies, all sorts of stuff. It does seem like the size of the black hole, or black holes, the black holes at the center of galaxies play an important role in the morphology and how they develop.
Right.
It seems like is there a design component to this that if you don't have these early massive stars, you don't get black holes large enough, you don't get galaxies big enough, you don't see the types of galaxies like the Milky Way. Is there that side of argument you can make, or is that pushing this too hard?
It's pushing it too hard, but I think it's going to come.
Okay.
I mean, let the James Webb do its work. I mean, that's why the paper ended saying, hey, we've done this with one little red dot. We need to do it with a bunch more. We do with a bunch more, we're going to be able to make those design arguments.
Okay, so it may well be the case. We just don't have the data that weighs in on that at this
Well,
point.
we got some of the data.
Okay.
I would say, hey, the fine-tuning evidence is better than it was 3 years ago. But I'm looking forward to making a much more definitive case than we can right now. So I'm basically telling people, let the James Webb astronomers do their work. I know you're all anticipating this stuff. It will come. And we can see that it's moving in the direction of giving us more design evidence. But yeah, I'd be cautious about pushing it
that's
at this
fair.
point. Yeah.
So two other questions, and they're both related, but because they're going at the same point. You said that skeptics like to use this to say, oh, Big Bang cosmology doesn't point to a beginning. Young Earth creationists like to use this to say that Big Bang cosmology is correct or is not correct. So, using this, how would you use this, or what would be your response to the young Earth creationists that say, the James Webb is showing the Big Bang cosmology
Well,
is
what
not
I'm
right?
seeing from young Earth creationist astronomers are saying, hey, James Webb is telling us the early universe just looks like the present universe.
Okay.
These discoveries are basically saying that's utterly false.
Gotcha.
The early universe looks very different than the present universe. And we can actually see that these galaxies are developing as the universe gets older and older in a Big Bang context.
Gotcha.
So now it is true that astronomers were saying in the early days of James Webb Space Telescope discoveries, galaxy formation doesn't appear to be going the way that we had presumed.
Right.
But that got interpreted, hey, the Big Bang creation model is not going the way that we presume. There's a big difference between
there really is,
how
yes.
galaxies form and how the universe forms.
Right.
So, the whole mission of the James Webb Space Telescope is to say, hey, we have a large family of Big Bang creation models. Can we actually narrow the scope of viable models? And already the James Webb has made significant progress.
Yeah.
We're basically tossing out all those models which stated, hey, we're not going to get any stars bigger than 200 times the mass of our star, the sun. We know those Big Bang creation models now are incorrect.
No,
So-
and I think your point is very important to bring up, and I'll just state it in a different way just because I think that may be helpful, is that prior to the James Webb, we have the cosmic microwave background radiation map, and then we've got the Hubble Ultra Deep Field and other instruments in that class that say, so we can see up to about 400,000 years after the universe started. We can see, maybe from 12 billion years on with the Hubble Space Telescope. We know you don't have galaxies at the end of when the cosmic microwave background radiation, but you do have galaxies by the deepest we can see with the Hubble. So somewhere in there, you got to form galaxies.
Right.
James Webb is just saying we have all these ideas of how galaxies formed, and the simplest models were, kind of just basically linear growing, if you will. All James Webb is doing is saying we can actually now see what's going on in there so that we can find the actual how it's going on instead of having to extrapolate or interpolate between the two. And every time science has done that, it's always been weirder than what we expected. I think your point about how looking at this and saying, oh, James Webb is showing that the Big Bang model, it's just not how science has worked.
You're bringing up an apologetic point. If you use the word weirder, I prefer the word more complex.
That's fair.
I mean, that's what happens. It's always more complicated than what we thought. And that extra complication yields design evidence. So we're going to find more fine-tuning, more design. The other thing I think is important to bring out is to note that the Bible stands alone amongst books from the ancient world that actually predicted that the universe would have Big Bang characteristics. So the fact that we're getting a stronger case for Big Bang tells us, hey, for getting a stronger case that the Bible indeed is inspired and inerrant.
So you're kind of weighing in my other question. Okay, here's how you would respond to the young Earth creationists. How would you respond to the skeptic that says, the scientific data about Big Bang cosmology, James Webb is showing that's not the right way to look at it?
Well, a couple of days ago, I debated, two atheist cosmologists who were coming up with all these different Big Bang models. And but what I noticed was they did agree, hey, it's some kind of Big Bang, but it could be a really weird Big Bang. And James
is that weird in my definition?
Weird in your definition,
okay,
right? I mean, they were saying, maybe there's an extra dimension of time, maybe two extra dimensions of time. Maybe the velocity of light is 1 billion times faster.
Right.
Maybe we have different laws of physics in the very early universe. And, it was enjoyable for me about the debate. Those are the same questions we were addressing in a conference at Cambridge University, where we had 16 Christian scholars, 8 physicists, 8 philosophers, and we're saying, how did God create the universe? And we were basically bringing up the identical models that these atheists are bringing up.
Right.
Making the point, hey, one of the things the Bible says about Big Bang cosmology is the universe we can detect did not come from that which we can detect. And of course, God has given us the ability to speculate about all kinds of things we can't detect. But James Webb, and I said, okay, we have all these speculations. What can we do to constrain them? And so, my background is observational cosmology. What can we do to, kind of say, hey, these models, speculative models are worth studying. These are not, because observations are constraining. And James Webb is in a position to provide stronger constraints.
Right.
So we're not going to get the ultimate answer because we're probing before that moment when we can detect things. So, but it's still fun. It's enjoyable. In fact, I use that as an argument for God. The fact that God gave us human beings the capacity even to do that tells us there has to be a God. So, because my dog doesn't do that.
No, that's a fair point. And if you don't mind, that provides actually an interesting transition to what I was going to talk about, is because there's a paper published by, just read the names here. It's Mir Fazal, Lawrence Krauss, Arshid Shabir, and Francesco Marino. And the title is Consequences of Undecidability in Physics on the Theory of Everything. And what's interesting about this, or what I found interesting about this, is this idea.
Can you tell me where they published it?
It's a journal. It's kind of an odd name. It's the Journal of Holography Applications in Physics. So not your not your standard
not your standard
journal, Daryl. But it's dealing with some things that in very real ways would be metaphysical, if you will. And so it's not here's observations we can make, but it's got a much more mathematical component.
There's plenty of holographic Big Bang models out there. So
fair point. And that's one of the things. I was reading this, and the bottom line, as best I can tell of what they're saying, is that scientists are looking for this theory of everything, and I'll explain why, some of the components of that, where you write down these few laws and then mathematically, basically you calculate everything based on those laws, and you can describe everything that's out there. That's what this theory of everything is supposed to do. And there's really good reasons motivated why we ought to be doing this. But the bottom line they're saying is you can do all that, and there is they can mathematically show that there is a component of our universe, or components of our universe, that are non-algorithmic. That you can't, which means that you can't write down some axioms and then calculate everything. And the conclusion they draw, which I think to the extent their mathematical formalism is correct, is that our universe cannot be a simulation because there is non-algorithmic information. In other words, there's stuff that's true about our universe that we can tell is true that isn't calculable from a set of axioms that are there. And I thought it was really interesting because I know Lawrence Krauss is a well-known skeptic and not a Christian. In fact, his book Universe from Nothing is very it's not complimentary towards theologians or even philosophers at some level, to say the least. And so I found this discussion very interesting because I'm looking at this and saying, yeah, that's exactly what I would argue as a Christian. It's that science has, or the ability to calculate and quantify what's out there. No doubt there are great tools we have as humans to do that. But I think as a Christian, I would say, yes, science has this great tool, but it's not the answer to everything. And it seems like there's this component they're getting at of saying, oh yeah, science still can be the answer to everything. We just have to incorporate this non-algorithmic understanding. And I'm like, as a Christian, that's exactly what I'd been saying. It's like, yeah, science, this calculable part or this algorithmic part of science is great, but there's more to it than that. And so I think there's some really interesting philosophical and theological connotations in there, but I just find it interesting that here I think two of the people on this paper are strong, outspoken skeptics, and they're writing a paper. I'm like, yeah, that's exactly what I would expect as a Christian if the God of the Bible is who he says he is.
Deja vu. It's kind of like my experience a few days ago with
Exactly.
these two cosmologists. Hey guys, we're all on the same page.
Yeah, we've been talking about. Yeah, we may not be so different after all.
Right.
What I do think is interesting, an interesting aspect of this paper, because I wrote a book, Escaping the Beginning, and one of the things that plays out in there, or one of the explanations offered for all that we see, is that we're just a big simulation, and so if we're complex life, looking for life out in the universe. When you start talking about the multiverse, one of the things you have to deal with, or the fact that life exists, you no longer get to say, well, there's this organic life that developed on a planet and has this long evolutionary history. If you're talking about the multiverse and using the multiverse to explain improbable because everything that does happen can, or everything that can happen does happen, you now have to ask the question, what other kinds of life could there be? You get into Boltzmann brains, but one of those ideas is that there are civilizations out there running very complex simulations of universes. And the question is, are we one of those simulations, if you will? And what they're arguing, what the outcome of their mathematical reasoning is that if there's this non-algorithmic component that is necessary to explain what we see in our universe, then of necessity we can't be a simulation, because there's things that we know are true or can say are true in this universe that are not derivable from algorithms. So it can't just be a simulation, because a simulation is here's the input, here's all the algorithms, just calculate. And they're saying, no, there's got to be something more to our universe. And it's not so much science in that it's, okay, here are the observations we can make. It's looking at various mathematical theorems that have developed by Gödel. Gödel's incompleteness theorem says that for any sufficiently complex mathematical system, there are statements that are true that cannot be proven within that system. And, basically, the bottom line, or what comes out of that, is anything that this self-referential component where you can talk about yourself. And humans are the creatures on this planet that we know can think outside of themselves. And
right.
So that's this self-referential component seems to be an integral component of who humans are. But you've got Gödel's incompleteness theorems. You've got a fellow named Tarski who was talking about decidability of, can you decide what is true? And he's showing that any sufficiently complex system cannot justify the semantics on which it's built. So you go look at a mathematical theorem. You say, okay, here are these axioms. I'm going to build on this. Well, those axioms are just given in there. You can't decide whether they're true from within the system. You have to look at something outside of the system, and that's what Tarski's theorem effectively says. So even if we could build a mathematical system that could entirely describe our universe, we can't decide whether it's true based on the system itself, because there's just this incompleteness to it. And then there's also another question of, and this is where I think the tie directly comes into science, is that you can't even, there's a lack of ability to decide how complex you are, because any sufficiently complex or sufficiently long string or set of information, you have to decide, what science does. I'm sorry, I'm rambling a little bit here because it's a little bit hard to articulate. What science does is it goes in and it says, all right, as a physicist, I see a ball, shoot a ball, throw a ball. I could take an approach to say, all right, to explain or to account for or describe that, I will just take every possible way to throw a ball, do that, and then write out what it is. And I've given a description of the system.
Yeah, you can write algorithms for it.
Well, no, I'm not even writing an algorithm. I'm saying if the ball is thrown this far at this speed, it goes here. If the ball's thrown this far at this speed, I can actually write out everything, every particular instance. But that is the complexity of that system is not as large as it looks like, because that would take a lot of writing to do. What science says is, wait a second, there's actually patterns in there that we can extract. And by extracting those patterns, I can, with a very small set of equations, I can now describe all of those systems. So the system, even though it's this really long string of this ball went this far, this ball went this far, this ball went this far with all the different conditions, I can now encapsulate that with a far simpler equation. What this other incomplete is given a sufficiently complex system, you can't tell how complex it actually is. There's an undecidability in how complex it is. And all of that put together is what these mathematicians, physicists, philosophers go in and say, wait a second, given all of this, we can say definitively, mathematically show that in order to explain our universe or what we see here, there must be this non-algorithmic component, which means that there's, unless I'm entirely misunderstanding, there's something more to this universe than just the mathematics and all the axioms that we can put into it. There's got to be something more about that. And I think that's very interesting, because if I look at what Christianity says is true, that God is the creator of everything, that he has created the universe, he's fashioned the earth, there's an orderliness, there's a regularity to it, there's a purpose and a plan for it, that it wasn't perfect, it was designed to do something, and it's doing what it was designed to do incredibly, exactly the way God expected it to play out. And in the midst of that, he's created these beings who can relate to him, who have this capacity to step outside the physical or see outside the physical and see something bigger. We're actually aware of our place in the universe. These theorems, this development says, yes, this is exactly what I would expect if Christianity were true.
Yeah, so in one sense, what they're showing is that the universe is not just a set of algorithms, there's a mind behind it.
Exactly. And if that's true, it can't be just a simulation. And I think the implications of it not being a or just a simulation that's profound. But it also is really arguing what Christianity's argued all along, that there is this incredibly fascinating, highly ordered, incredible sophistication and simplicity and complexity in this creation that we can study and understand the patterns and recognitions, but that's just not all it is.
So these four authors, how much of the history of the universe did they apply this to?
They weren't even looking at, can we understand the history of the universe? What motivated the discussion was this, and I alluded to this a little earlier, is that we go out and we look at our universe and just go back, I'll go back 400 years ago. That's a little bit inaccurate because we didn't go back 400 years ago. We've got gravity, we've got electromagnetism, and we see those two things at play. And in fact, actually, we thought it was gravity, electricity, and magnetism. And what James Clerk Maxwell recognized, amongst others, is that, wait a second, what these two disparate phenomena that we thought were true, we had these equations we could write down to describe them. They're actually the same thing. That with a set of about 4 equations, you can describe a whole lot about electricity and magnetism. And so this very complex set of phenomena that would take a lot of pages to write down all of what's going on, with a very small set of small set of axioms, if you will, equations, you can now calculate a whole range, a very wide variety. There's an algorithm to predict a whole lot about what's going on in creation. Now, keep going with that. You've got electromagnetism, strong, weak nuclear forces. You've got the gravitational force. Einstein comes along and says, when we're talking about gravity, that instead of gravity being this thing where there's space and time and things just attract, no, it's actually more fundamental than that. That gravity space and time are actually deformable. Space and time are intimately tied together. It's not space and time, it's space-time. And beyond that, space and time are elastic quantities. They can change, and that radically changed how we thought about the universe. Now, what's interesting, or an implication of this, and this is something I've heard about you almost 40 years ago now, is that when you say, all right, if general relativity describes the universe and energy behaves a certain way, and with these relatively straightforward or reasonable axioms, if you will, you can show that the laws of physics break down and you need something beyond the universe to explain it. Space-time theorems of general relativity, or the singularity theorems of general relativity. That flowed out of Einstein's new way of looking at space and time. If space and time were just absolute entities that everything happened within, you don't get the singularity theorems of general relativity. But if general relativity is correct, you now get these. So now they're saying, wait a second, these singularities point to something beyond that. Can we look for a quantum theory of gravity that gives us a complete description of everything? And what they're showing is that these singularity theorems show that space and time is not fundamental. It has to come into existence. This quantum theory of gravity has to explain I'm drawing a blank, the formation or the generation of space-time, which means that something outside of space-time must be more fundamental. They actually argue that there's an informational component to it.
Yep.
And it's not just information in terms of axioms, but information in terms of this non-algorithmic information that's there.
Or as the author of the book of Hebrews put it, there's something beyond matter, energy, space, and time.
No,
the Bible said it
yeah,
2,000
exactly.
years ago.
It's like I'm sitting here looking at this paper, and it's a testament to the integrity of Krauss and Mirzal, Fazal, because I know that they are skeptical of Christianity, but yet they're generating this paper that very much aligns with what Christians have said for millennia, and I think that's fascinating.
Well, my wife came up with a similar argument when our sons were going through their teenage years.
Okay.
She said, Hugh, as mathematically trained as you are, there's no way you can develop a set of equations to predict the behavior of our sons. They're complicated.
That's a good point. No, exactly. No, and it seems like God has made this universe complex enough that He's made it complex enough that it's impossible to simplify it to a set of axioms, if you will. But He's also made it, He's given us the capacity to understand a lot of the algorithmic component to it. The error I would say we make is that because we have such success in developing the algorithmic component that we've decided that's all it is, instead of recognizing that, that is a powerful component, but that's just not all there is.
It's not all there is, exactly.
And I think that's just a very powerful scientific point, that God has seemed to have orchestrated this universe to give us great insight into things, but also to recognize that there's always a limit to what we know. I mean, these Gödel's incompleteness theorem, Tarski's undecidability theorems, this theorems about whether we can decide complexity, it doesn't say we can't do a lot. It just says we can't know everything. And even in the way God interacts in creation, there is a hiddenness to Him. It's like there's an abundance of evidence to support that He exists, but He's also hidden Himself so you're not compelled to exist, which if things were complete and decidable and you could map out everything, you would have no choice but to believe that. It seems like God's given us the capacity to have an actual genuine choice in the way He's constructed the very fabric of the universe.
Yeah, and it shows that a professor I had years ago, Fred Hoyle, who basically said the universe is all that there is.
Mm-hmm.
Carl Sagan said the universe is all that there is or ever will be. This is showing that's not correct. There's more to existence than just the universe.
Great, very well stated. I think that's true. One of the things I do think is interesting in their papers, they say, okay, there's this algorithmic component and then there's this non-algorithmic component. And the statement they made in there was that, and I'm going to miss the statement, or my paraphrase, what struck me about that was, it says that the fact that we have this non-algorithmic component doesn't mean that it's not science. And I wonder if that's a reflection of, if I could, I think maybe some of the ways that Christians have approached this is saying, the high skepticism of science, or even where Christians might have argued, well, we don't understand this, therefore God did it. And I think there's a lot of ways where Christians get beaten over the head with that, and I don't think we did that as much, but I do think there are times where we have done that, or Christians have done that. And my contention all along, or what I would have said all along, is that, yeah, science is this great tool to understand creation. It's just not all there is. That doesn't mean that as we continue to understand, that doesn't mean that we might not be able to explain more and more of what we thought maybe was the non-algorithmic component. It may very well be we think something is, just the way it is, or something beyond our explanation. As we develop, there may be more and more there. I'm not scared of that. In fact, I actually said that when people started talking, or prior to the multiverse becoming part of the scientific discussion. Prior to the Big Bang, anything prior to the Big Bang was outside the realm of science because we didn't have tools to discuss it. Well, when the multiverse started growing, my thought was, and I think I said this places, is that at some point the multiverse, which is pre-Big Bang, which was supernatural at the time, if you will, is going to become part of the natural explanation of our universe. And lo and behold, that's what's done. So we didn't have the tools to explore before the Big Bang. So prior to that was supernatural by definition.
Bottom line, what you're saying is science is advancing.
Exactly.
Yeah.
And it may be some things that we thought were unexplorable, we find later they can be explorable. And that these authors may be highlighting a way where there may be a lack of how we can approach things with an algorithm, but that doesn't mean we have to abandon science. There may be ways to investigate that. But I think if you take a scientism approach, that science is the only answer, you get into a problem. If you take an approach that pursuing understanding is a bad idea, you get into approach. But if you say, hey, let's understand things and recognize there are limits, but we don't know where those limits are. So things that are limits today may not actually be limits. We might get there. Keep working, keep pushing. That's where we get all of this abundant evidence for the support, or that we at RTB use to argue for God's existence.
Well, where did our curiosity come from? Where did our desire to push the boundaries come from? So
I agree. I think that's a God-given ability. And there's an interesting part of this that I did some podcast with Kyle Keltz a while back where we talked about the various of the 5 ways, and I think it was 2 and 5. And I never, there's a philosophical richness to that I always, unless I prep well for it, I always miss in there. But I do remember we had this discussion of there's different types of causes. There's efficient causes, there's formal causes, there's final causes, and I'm missing what the material causes. Part of one of the points that was brought up in there is that when we were talking about these causes, part of how science really was able to move forward is to say we're not going to concern ourselves with the final and the formal causes. We're just going to concern ourselves with the material and the efficient causes, because those are the things that we can quantify that are susceptible, or that can be described by algorithms. And I'm just wondering here, maybe what we're now doing is where we were able to say we need to get all 4 causes put together at the start was too big a task. We made it a smaller task, and we could do efficient material causes very well with science. Now maybe we can expand science to talk about what may be these formal and final causes, which may be that non-algorithmic component that's in there. And so where scientists can kind of think lightly of philosophers, it may be that science was only able to advance by saying we can't deal with all of what philosophy can deal with. We're going to have to make it a smaller piece. And as our understanding grows, we may be able to incorporate and include what philosophers have thought all along.
An example of that is one way we can explore the beginning of the universe is to look at how the universe will end. So
it flesh that out a little bit.
Well, in the sense that we develop models. We know what's happening in the universe today. And there's various models that tell us as we extrapolate into the future, X, Y, Z may be possible. Mm-hmm. And if we can determine which one of X, Y, and Z is possible, that's going to give us some constraints of what was happening in the beginning of the universe. So it's like, that's something that actually came up in the debate we had a few days ago, is that one of the ways they make some headway and all these speculative models about what was going on before the Big Bang, let's see where the universe is going to go.
Right.
We can nail that down. And I'm not all that hopeful we'll be able to nail it down, but we should be able to eliminate a few possible speculations. If we can do
that's
that,
fair, yeah.
that might help us eliminate some speculations what was going on at the cosmic beginning. So
like I said, I just find it, at the end of the day, the title of the article is "Physicists Prove the Universe Isn't a Simulation After All." I think that's a big step forward. And if there's this non-algorithmic component, it seems pretty convincing that that's the case.
now, is that going to spoil people's enjoyment for the Matrix film series?
I don't know. I like I believe Christianity is true all along, and yet I enjoyed the Matrix at the same time. So,
Okay.
so I think that's a different question.
Well, that's another argument for God, actually. Notice we humans enjoy fantasy. Things that are
Interesting
not
point.
true.
No, that's a good point.
My cat and dog don't,
Right.
but we humans are compelled to engage in fantasy. And
It's interesting too. As I was just kind of exploring and trying to understand well enough, Gödel's incompleteness theorem, Tarski's undecidably, that these theorems, there's just a lot of math in there. And I remember seeing a fair bit of it in college and kind of thinking more about it. But one of the arguments, there's a Lucas Penrose argument, which is related to this Gödel's incompleteness theorem, because for any formal system, computational system, if you will, there's at least one statement that is true that cannot be generated, and it's called the Gödel sentence. And this statement cannot be proved within, or can be shown within. And if the idea behind it, and it's that self-referential component, is that if it's true, it should be generated, but if it can generate it, it's no longer true. And the point they make with that is not that you can come up with these weird sentences, it's that the algorithm or the computational algorithm cannot show that the statement's true. But as humans, we can look at it and say, yes, we know that's true.
Yep.
And so there's something we're capable of doing that formal system isn't, or that formal or that computational system isn't. And you could just say, well, okay, so why don't we just put that into the system, put it in as an axiom? Well, now you've got a different formal system, and there's a Gödel statement for that. And for that, and so kind of ad infinitum. And even if you generate an algorithm that generates the system, it seems like you end up in this case that whatever you have in there, or whatever formal system you start with, there's always there's a true statement that cannot be generated within the system. And I was just thinking about that, the implications of that. Either you've got this infinite regress or infinite progress, because it's not a progress. It's for every system I can generate a Gödel statement, so I include that. So now there's a new system. It does seem like there just needs to be something that is just a necessary being. It seems like this is what philosophers were talking about when you have necessary beings, because computational has this could be other, could be, it's always derivable, it's contingent, if you will. But there's just a lot of philosophy packed in here that philosophers have thought about for hundreds of years that seems to be kind of new to the scientists, if you will. And I think there's a little bit of scientific arrogance, and I will say this as a scientist, that I sometimes fail to appreciate the depth of understanding that philosophers have developed as they've looked at the world and thought about how to put things together, even though I would argue that's also not a complete system either.
Well, Gödel came up with his incompleteness theorem in 1930.
Right.
And it was philosophers that first responded to his theorem.
Yes.
And several of them who were Christians are making the point. The core of the conclusion from the incompleteness theorem, there has to be something beyond the universe.
Right. Yep.
And so,
well, and the implications just even of that little place, it says if it's correct, then it will say that this artificial general intelligence is not possible. If artificial general intelligence is defined as can do things the way humans do them, because that presumes that humans are a computational system only.
Only, right.
I just find it interesting that this applies to whether the universe is a simulation, what is the ultimate reality, but it also applies to humans, which to me gives further evidence that we are created in God's image. We're not just like all the other animals. There's something unique and distinct about us because we can think about things like this.
Well, Jeff, because of this past hour, I'm now convinced you're not a simulation.
You know, I am so glad to know that, Hugh. I never really had that concern with you, but all right, I appreciate it. Hope you enjoyed the dialogue between Hugh and myself today. I want to encourage you to drop down into the comments below and join the discussion with us. Let us know what you think. Remember to like this video, subscribe to our channel. We release new podcasts each week here on YouTube and on your favorite podcast app. Remember to share this video with someone else, have a great conversation with them, and remember, the more we learn about science, the more reasons we have to believe in the God of the Bible.